So I'm going to clear the event horizon so it's safer for me to be on one side of the stage than the other, and give way to Professor Chris Lintott.
Thank you very much. Thank you. There are places in the universe which are cut off from us, forbidden regions, which once entered can never be escaped. Once believed to be a myth, we now know that these aren't just a mathematical trick made by torturing equations, but these places are both common and they're influential in controlling the story of our cosmos now, in the past, and for the rest of the time that the universe will exist. What happens inside them remains a fundamental mystery. Our equations, our physics that's normally so good at describing how stars move or capturing the fall of an apple or even measuring the expansion and evolution of an entire universe breaks down in the exotic conditions that live within these objects. And only the bravest physicists, not me, delve into these regions, resorting to fevered talk of wormholes and firewalls, of singularities and infinities to try and make sense of what their theories are telling them. But despite this fearsome reputation, these objects, which were once called frozen stars, but which we'd now call black holes, they pose no threat to us. Despite what popular culture tells you, despite all the science fiction you've seen that says you should worry about these things, I promise they're friendly. I'm going to found one day the Black Hole Rehabilitation Society, and we will learn to love them. They're just everyday working pieces of cosmic machinery, part of the cosmos that's shaped by gravity, the same gravity that influences the galaxies around us and the solar system that we live in. What's fun, though, is that despite their mystery, we're finding really new, ingenious ways to peer into these dark objects. For example, at the center of our galaxy, there's a cluster of stars. And using a technique which allows us to get pinprick sharp images of that region, we can now resolve individual stars at the center of the galaxy. The white thing in the middle has been added. That's a marker of where the center of the galaxy are. The stars are the blobs. But over time, and there's a year in the top right here, you can see that those stars move, and we can watch them move, and they're in orbit around a black hole that we can weigh at 3 or 4 million times the mass of the sun. And just to reinforce the fact that black holes are friendly, these stars are not in danger. They're not falling into the black hole. It's not going to suck them in like some sort of cosmic hoover. They're in orbit about this object just as the Earth orbits the sun, and we'll see later how that works. But there are other ways of detecting these things as well. Take last Sunday morning, for instance. I didn't sleep well at the weekend, mainly because I was trying to work out how to start this lecture. And so at about 5 in the morning, I was half awake and tossing and turning, at which point the dog, who incidentally isn't allowed on the bed, got up, got fed up of me, stretched and buggered off. There he is, that's my token dog photo. But at the same time that happened, it turns out that a disturbance in space, actually in space-time, but the distinction won't bother us this evening, passed through the Earth, a ripple in space itself. It lasted less than a second. It traveled through the Earth without me noticing, without, as far as I know, the dog noticing, unless he's got some very special physics powers. But it was captured by an astonishing worldwide network of specialized observatories that were set up to detect just this phenomena. I know it happened because they issued an alert, and if they're right, if this turns out not to be a false alarm, and as we'll see, this is a tricky business, we were detecting the signature of an event that happened hundreds of millions of years ago in a distant galaxy when something really spectacular happened. And this kind of observation has nearly become routine. Astronomers have got good, physicists, engineers, the teams have got good at doing this. Take 29th of December 2017, for example. This is an image of a galaxy called NGC 4933. It's only 130 million light years away, so relatively nearby. It's a fairly ordinary galaxy. It's quite beautiful. You can maybe see there are dust shells. Maybe it's had a merger recently. But in this galaxy, on that particular day, a satellite in orbit called Fermi that's sensitive to high-energy radiation picked up a flash of light. And that was quickly echoed by other telescopes, by telescopes sensitive to the X-ray. For example, this is ESA's XMM satellite, picked up an X-ray flare, but also from the ground, this is a picture in optical light, and the type of light that you and I can see. We can visualize what's going on in this event. We think it's what's called a kilonova, which is what we call a supernova, the death of a massive star when it's really spectacular. We've just decided to invent new terms. There's no distinction, really. And we can make really pretty animations about what's going on. So obviously this is a computer animation. But what's happening is two compact objects, these are neutron stars, the cores of massive stars, are in orbit around each other. They spiral together and they collide, releasing that flash of high-energy radiation and then a jet of material. And what you're seeing here in blue and then in yellow is the different types of light that we detect from this object. This is the kind of thing astronomers do all the time. We've talked in these lectures before, and I will talk again about our love of the transient universe, of seeing things change in the sky. But if I play the start of that video again, then I want you to notice that something else is happening. We've got two objects in orbit around each other, and then they spiral together. They must be losing energy. And what's happening is that they're losing energy by emitting what are called gravitational waves. These are those ripples in space-time that I spoke about. Whenever anything massive moves in the universe, it turns out that that object emits gravitational waves. Now, I'm a massive being. I am moving in the universe. I can move dramatically. And in theory, I've just emitted a gravitational wave and lost some energy by doing so. But space is stiff. And I mean that really formally, in that you have to really whack it to get a wave to move through it. And so this phenomena only really happens, is only really noticeable when very massive objects move very fast. So for example, when you have two neutron stars, both of which are several times the mass of the sun, when they're close enough that they're orbiting at hundreds of kilometers a second, they begin to lose energy through gravitational waves, and then they combine and explode in a kilonova. And indeed, the gravitational waves from this object were detected at the same time that that flash of light arrived, leading us to the wonderful conclusion that we've measured the speed of gravity. It moves at the speed of light, which delights my physicist's heart, and perhaps yours too. But also, the fun thing was that by putting together the different sets of data, astronomers were able to reach a conclusion that has everyday consequences. So if any of you are wearing gold or silver jewellery this evening, or if you have some at home, the gold and silver in the ring or the earring that you're wearing comes from a collision of neutron stars like this. We've seen it forming. And so bits of precious material we have on Earth comes from this very exotic, unusual source. You have a connection to these cosmic explosions. Now, the idea of gravitational waves is an old one. It goes back to more than 100 years to Einstein's theory of general relativity. And the general theory describes how gravity works. Einstein had come up with a special theory of relativity, realized gravity didn't fit it, and then created a general theory published in 1916, which described how gravity affects the universe. It fiddled with Newton, basically. It actually solved some problems that Newton had left, and which physicists have been used to thinking about for a while. For example, that in Newtonian physics, gravity happens instantaneously. So the moon is in orbit around the Earth. We have a set of equations that describe that, but it's assumed in the Newtonian theory that somehow the moon is feeling the Earth's gravity instantly. There's action at a distance, which doesn't really make much sense. Newton was aware of this problem and said that it worked anyway and that people should stop worrying about it. I'm paraphrasing, but not by much. General relativity solved that, and it gained prominence and fame in 1919 when astronomers, including Eddington travelled to see this total solar eclipse, and they measured positions of stars, which you could see circled here, and those stars had moved very slightly from the positions that they normally have when they're not behind the sun. And the interpretation, which makes sense in general relativity, is that the mass of the sun had bent the path that the light was taking, so that the stars appeared to shift in position. There's a more general form of this you've probably seen if you've gone to enough physics lectures or seen a particular episode of The Simpsons or whatever. You're used to seeing space represented as a grid, and then you put bowling balls or things in and it bends. And this is the fundamental insight about how gravity works from general relativity. The great physicist John Wheeler, who we'll meet again in a second, said that the essence of general relativity was that space-time tells matter how to move. So the geometry of space, where it's bent, matter moves differently. If you rolled a marble across this sheet, it would follow the contours that dip into these gravity wells. So space-time tells matter how to move, but matter tells space how to curve. So when you have a mass, space bends around it. That's why those stars in the eclipsed sun had moved. And so you can see in this space, if one of these massive bodies moves, we should expect a wave. If I throw something onto this sheet, we might get a ripple moving outwards. And Einstein and others realized that this was a consequence of his theory. He published a paper in 1916 saying that gravitational waves shouldn't exist. And he published one in 1918 that said they should do, but it wasn't clear that anyone at the time thought this was a real effect, anything other than a mathematical trick, essentially. Certainly, no physicist writing at the time in the early 20th century would think that this was an observable phenomenon. Actually, general relativity as a whole was treated almost as an afterthought. It was a mathematician's plaything, not a tool for doing physics in the real universe, not until the mid-50s and 60s. However, gravitational waves exist, and we can measure them. And we realized this early on in 1974 when a pair of astronomers, Hulse and Taylor, discovered what's called a double pulsar. So again, this involves these neutron stars, the dense cores of massive stars, supported by some quite strange physics. And around these neutron stars, you can have a strong magnetic field, and when that happens, you can have material emitted in a jet, moving very close to the speed of light. And because these things are spinning rapidly, in the case of the Hulse and Taylor discovery, one of these pulsars is spinning once every 59 milliseconds, then that jet swings around. And if we lie in the way, we pick it up with radio telescopes. It's what's called a pulsar, the great discovery of Jocelyn Bell Burnell about 15 years earlier than Hulse and Taylor. Hulse and Taylor found a pulsar using the Arecibo telescope in Puerto Rico, the much missed Arecibo telescope in Puerto Rico, star of James Bond, amongst other things. And it didn't get top billing for some reason. But they discovered there's something odd going on. So they had this pulsar that was pulsing every 59 milliseconds. But over the course of every 8 hours, sometimes the pulses would arrive early, and sometimes they would arrive late. And there was this pattern that repeated every 8 hours. And what they realized was that that pulsar had to be moving in an orbit. And so when it was closer to the Earth, they got early pulses. And when it was further away, they got later pulses. And there was this 8-hour cycle. So they knew that it must be in orbit around something else, another massive object. So we now have 2 neutron stars in orbit around each other, and I've already given away this punchline. What happens is that they're spiraling in towards each other because they're losing energy through these gravitational waves, these ripples in space. Here's the real data, going back to about 20 years ago. The system, just through these gravitational waves, is emitting about 2% of the power of the sun. And they're spiraling closer by 76 microseconds a year, which isn't a lot. They're getting 3.5 meters closer a year. And if you hang on for 300 million years, there's going to be a spectacular explosion when they collide. In the meantime, we have to satisfy ourselves with this beautiful graph and the fact that we can see the effect of the gravitational waves. You can calculate Black line here isn't a fit to the data. This is a calculation of how this system should be behaving if gravitational waves exist. I remember doing this in my undergraduate physics, and it was a beautiful result. To explain something that's seen in the universe so clearly was genuinely excellent and wonderful. Now, this is an indirect detection of gravitational waves. It would already have astounded Einstein, but we want to go further. We want to see these things directly. And so there were attempts in the 60s and 70s to build what now seem quite bizarre experiments in order to try and discover these gravitational waves. A physicist called I think it's Weber, it would have been Weber, at the University of Maryland, had these wonderful experiments in the 1960s and into the 70s. So he had these giant aluminium cylinders. You can see one here. He worked with between 5 and 10 of them. So you have to think of this as an enormous xylophone. And it was tuned in the hope that if a gravitational wave of a particular frequency, a ripple in space like the one that maybe disturbed my sleep the other Sunday, came through, these would ring very quietly. And then the band you can see there are sensors designed to detect that rigging. So what you're expecting as the gravitational wave comes through is for the cylinder to be squeezed and stretched, rather like this schematic diagram, but on a much smaller scale. Now, Weber thought he'd discovered things. He kept seeing patterns that he thought were the result of gravitational waves. But his experiment was incredibly sensitive to any sort of movement in a theme that runs through gravitational wave astronomy. The effects we're looking for are very, very small. Even large gravitational waves, say caused by objects that are 30 or 40 or 50 times the size of the sun, the mass of the sun colliding, that will produce a displacement on Earth of something like a 10,000th of the size of a proton, a billionth of a meter or something like that. So these are incredibly tiny effects, and almost any other movement, a truck 10 miles away, somebody knocking on a door down the other end of the corridor, a physicist moving, was likely to induce false signals. And so Weber's results were not successful, but they inspired a bunch of other astronomers to use a different technique. And I'm going to try and explain this with the help of some of the people in the audience. So can we have the house lights up, please? Now, some of you have got pieces of card under your chairs, mostly people over here. If you have a piece of card under your chair, could you grab it and stand up, please? And I can show everyone what's happening here. Very good. There should be 2 rows of people. If you've got a piece of card, please stand up. I promise I'm not going to ask you what you do for a living or anything like that. Okay. Now, 2 of you should have cards that say, "This is a mirror." Can you wave at me if you've got a mirror? Great. Okay. And, sir, down here in the corner, you are going to be a source of light. Okay? And so when I say go, what I want you to do is wave your card in the air and then put it down. When you've done that, the people on your left and behind you are going to do the same thing. And we're going to have a wave going backwards. So you want to look to in this row, you want to look to the person on your right. Here, you want to look to the person in front of you. When they take their card down, you put your card up. And we'll have a ripple that goes in both directions until you hit the mirrors, at which point you bounce off the mirror and we come back. And I want to see who reaches our source of light first. Is that clear to everyone? This may not work. Good. Okay, I'm going to count you down from 3. Ready? 3, 2, 1, go. Okay, so the waves are off. They're going at different speeds, so that's interesting. Okay, they're coming back from the mirror over here. Good. Okay, keep going. All the way back. Yeah. Oh, no, we've got a delay. That's fine. So obviously the physics is complicated here. So we're back once, and then the second wave comes back. Good. Okay, a good start. But the waves moved at different speed. So you're really terrible at being light. In relativity, light always moves at the same speed. So what we'll do is we'll give you a clock. I want everyone else, say on this side, everyone else in the audience, can you just applaud at about this speed, please? Just clap along with me. Okay, so you're going to raise and lower your card on a beat. Ready? 3, 2, 1, go. There, 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 there. Keep going. There you go. Back twice. Nearly. That's Duke. Excellent. Thank you. Give yourselves a round of applause. And you can all sit down. So what happened was the 2 waves arrived at slightly different speeds. And they arrived at different speeds. We should have predicted this because the distances were different. It's a shorter distance over there than it is to the back of the hall. And so what happens is that the two waves come back at different times and they interfere with each other. If we'd had the right speed and the right distance, they would have come back and hit at exactly the same time. And so that's the experiment that we do. I've said many times in these lectures that what I love about astronomy is that it's about making complicated measurements very well. And that's genuinely all there is to this Nobel Prize winning experiment. What we do is we do it on a grand scale. So this is Virgo, this is in Pisa, and our source of light is in this box at the center, and then there are two vacuum tubes with some of the the cleanest vacuum in the world that stretch 3 kilometers in either direction. And what we do is we send a laser beam into a system in this box at the center, split it into two, and send it off at precisely the same time, 3 kilometers in either direction. At that point, it hits a mirror, and it comes back, and as long as we've measured everything correctly, to an insane level of precision, then the two beams of light will arrive back at exactly the same time. If a gravitational wave passes through, then one of the arms, the stretching of space, will stretch one of the arms. And so what will happen is that the light will take slightly longer in one direction or the other. And if you can spot that, then you've detected a gravitational wave. The only problem is everything else that's happening. In particular, I've chosen Virgo here. There are 4 of these things. There's Kago in Japan, there's LIGO in Washington State and Louisiana in the US, and then Virgo. But I've chosen Virgo because they have Pisa Airport is at the end of one of those. So they detect planes taking off. There's also a motorway at the other end. It was built there for convenience rather than because it's a clean environment. The American ones, LIGO, are out in the middle of nowhere where it's easier. But the physicists go to great lengths to carry out this simple experiment really carefully. To give you an idea, and I'm not going to try and explain this, this is the input of the laser. This is a device known as a quantum squeezer, which helps control the uncertainty in where the pulse of light is. This alone took something like 250 PhDs worth of effort to develop and then install and run. And still, when you've done this with your gravitational wave observatory, mostly what you find is noise. You can plot the response of the system. You've got a frequency, so how fast the apparent wave is moving, and a time. And you get all sorts of interesting patterns. I really like the fact that the scientists give them names. The one in the top left is called a koi fish event, because it looks a bit like, I guess, a face-on fish. And the one in the bottom right is just called extremely loud, and is associated, I think, with doors slamming in the facility. My favorite one of these, so part of the game is to carefully characterize all of these sources of noise. My favorite one is that at LIGO in Washington, you have a vacuum tube 4 kilometers long, it's cooled, and so water ice forms on the outside of the tube. And the local ravens have discovered this is a great source of water. So they fly in and they peck the instrument rhythmically, thus creating an apparent gravitational wave. So you have to get rid of the ravens and everything else. And the only reason this is plausible is that in the 30 years that the team were developing this technology, theory was also progressing. There were advances in how to solve Einstein's equations and how to solve them on supercomputers that let people build really sophisticated models of what happens when, in this case, 2 black holes spiral together. So this is like the neutron star example. You've got 2 massive black holes. I think there's a 4 solar mass and an 8 solar mass here. They're rotating together. The green is a visualization of the gravitational waves. And you can see that they speed up and then they collide. And there's this point when they collide, it's called the ring down, where you get an effect like dropping a duck into a pond of water, where you suddenly get these ripples that spread out. I'll just play that again, because there's 2 sets of physics here. So the first thing is that the spiraling in starts slow and then gets faster, which means that if we are expecting a real gravitational wave signal, then we should expect something that starts off at low frequency and moves to high frequency, because that's the pattern of this spiraling in. And then there's this moment that's coming up right now where you suddenly get this ring down. And a lot of the physics that we want, a lot of our understanding of what these black holes are doing comes from that moment, from the ring down. And so, slightly to everyone's surprise, starting in 2017, we've been able to detect these things. Here's one example. And I'm showing here results from the 2 American observatories plus the one in Italy. And what you can see is that we've got these chirps. So we go from low frequency to high frequency. And there's a really clear detection at Hanford, one at Livingston, and maybe there's something there in Italy. And the point of having several of these observatories is that if you see the signal in more than one, you gain confidence that it's real. We actually know that it should be slightly delayed because this is a passage of a wave across the Earth. And so we can gain confidence that these are real. And we can have fun with this. So I've described them as a chirp. For once, we can actually play this as sound, and it's not cheating. So I'm going to play the sound of the first detection at its real speed, and then I think we slow it down. So you'll hear it in both channels from the 2 American detectors. That chirp is the moment where the 2 black holes are speeding up and colliding. And if you're a proper gravitational wave physicist, you could do an impression of all sorts of different black holes and delight your friends this way. But hopefully you could hear that. The point is it's a characteristic signal that we know to look for. And different types of collision produce different types of signals. So for example, the neutron star collision that I talked about, the one that produced the gold and silver, is a much slower event. Because the masses are less massive, they take longer to spiral in. And so it's already in the data. I can't hear it yet. This is 100 seconds worth of data sped up, and you'll hear it right at the end, that final point where the 2 neutron stars collide. Here we go. There you go. Hopefully you heard it. If not, I will play it again at the end. The other trick you could do is that because you've got 3 detectors, you can work out where on the sky these things are. Not to any great accuracy, but we can begin to say which patch of sky they come from. LIGO's been running ever since that first detection, and has now built up a library of collisions, which we can visualize here, because one of the things you can get from the type of chirp that you hear is the mass of the objects that's colliding. And so what's really interesting, in this slightly strange diagram, what we've got here is each event is represented by 3 points, the 2 original black holes or neutron stars, and then their product. And what you can see is that typically in blue, the black holes seem to be 10, 20, 30 times the mass of the sun, and they collide with black holes that are about the same size as them. So the universe likes creating black holes that are a few tens of times the mass of the sun. And we think we know how that happens. Those are created in the supernovae, the explosions that mark the death of the most massive stars. At the bottom, you've got the neutron stars. These are the dense bodies, the things that make pulsars. They're 1 or 2 solar masses. They're made in less massive stars where the collapse at the end of a star's life doesn't go all the way to producing a black hole, but produces a neutron star. And in between, there's this mass gap. There's this region where there don't seem to be many things. And we think there's a gap between the most massive possible neutron star and the least massive black hole. The 2 things are separate. Also, we thought until about a year or so ago, where we started to find things that overlap. The observatories have been made more sensitive, and there was an event called GW230529. They made this friendly greetings card from this event for you. They do this for most of their alerts. It's really rather charming. They say, okay, so what's happening here is we've got something 1.4 times the mass of the sun and something 3.6 times the mass of the sun. So it's the most equal partnership we found so far. And they appeared to have combined to form something that's about 3 or 4 solar masses. It was 650 million light years away, and there are lots of these. So we've actually ended up filling in this mass gap with things where we don't know what they are. We don't know whether they are black holes. We don't know whether they are neutron stars, but we're sure that we're measuring the mass. So whether this result, this sort of gap that's in here will hold, or whether we're going to have to change our theories of how these compact objects form and evolve, we don't know yet. We can also find out other things about the black holes. We know that most of them are spinning. And we know that because they drag space around with it. Remember, massive objects change space. Matter tells space how to bend, space tells matter how to move. And so we can distinguish between a black hole that's not spinning and one that's spinning rapidly by the effect on space and therefore by the shape of the gravitational wave profile that it sends out. Most of these black holes are spinning. That tells us something about how they form. We need to put that into our models as well. And that's about all we can find out about these black holes. There's a very stupidly named theorem called the no-hair theorem. I don't know why it's called the no-hair theorem, but the statement is black holes have no hair. And what's meant by that is that from the outside of a black hole, you can only ever determine its mass, its charge if it has one, and there's no evidence that any of these have charge, like electrical charge, and then its spin. So we've ticked off 2 of the 3 things you can know about these black holes. But that's a lot. And I think I want to make sure I've said that this would have astonished, again, many of the physicists who worked to develop the equations that we use to describe these things. People like Carl Schwarzschild on the left there with the magnificent moustache, a man who was one of the first to get to grips with Einstein's theories, who solved equations while on the front lines of the First World War and died from a disease he contracted on the Russian front. But he found a solution to Einstein's equations, a thing that's allowed by general relativity, that described this massive single point that one could orbit, what we would call a black hole. But again, no one was really sure they were real. There was an argument between Chandrasekhar and Rutherford, 2 great physicists later on in the early part of the 20th century. And Rutherford stated, I should explain, Rutherford was somebody who really understood general relativity. So he was approached after a meeting of the Royal Astronomical Society by somebody who'd said, I want your opinion on general relativity because you must be one of 3 people in the world who properly understands it. And Rutherford looked a bit confused and his questioner said, oh, come on, don't be modest. He said, I'm not being modest. I'm trying to work out who the 3rd person is. Anyway, so that's Rutherford. But he said that there should be a law of nature to prevent a star creating these black holes. Even in the 50s and 60s, John Wheeler on the right here, looking slightly quizzical, who worked on the physics of these things, didn't really think that they'd be represented in the real universe. Even at the time when pulsars were discovered and neutron stars were known about, people didn't think black holes existed. Wheeler, by the way, is almost the person we owe for the term black hole. They'd been known until that point as frozen stars, mostly by the Russian theorists who were working on them. And Wheeler was calling them gravitationally completely collapsed objects. And he was giving a talk at a conference, and he kept saying, gravitationally completely collapsed object. The gravitationally completely collapsed object will have the following form. And what's interesting about these gravitationally completely collapsed objects is there's this voice from the audience that said, just call them black holes, and so he did. And that's where the name comes from. But it wasn't until the 1970s that people realized these weren't a sort of mathematical trick, but were real features of the universe. So the first evidence really came from X-ray telescopes. This was a small X-ray satellite on the right here called Uhuru. Bruno Rossi, who's a famous X-ray astronomer, and Marjorie Thompson, who managed NASA's small satellite program, looking at the telescope. This is back in the days when they let astronomers get hands-on with their instruments. These days we tend to look at them through a window while the engineers deal with them. This was one of the first telescopes sent into space sensitive to X-rays. And it discovered a source of X-rays in the constellation of Cygnus that we call Cygnus X1. This is a more recent X-ray photo of it from the Chandra Observatory. And what was weird about Cygnus X1 was that it shone brightly in this energetic form of light, but it flickered. It flickered fast. It flickered on the scale of milliseconds. And what that tells you is that whatever's emitting the light must be small, because to change rapidly, you have to be in contact with the whole emitting region. And so if something's changing on the scale of a millisecond, it can't be more than the time it takes for the speed for light to cross a millisecond across. And so it works out this thing must be only a few hundred kilometers across. So they knew that there was something small, a compact object that was emitting these X-rays. And then they found from optical telescopes that whatever this source of X-rays was, it was being orbited by a star. What that means is you could work out its mass. And it worked out that this Cygnus X1, whatever it was, must weigh 15 times the mass of the Sun, but be only a few hundred kilometers across. And we know from physics that that is going to be a black hole, that you can't cram that amount of material into such a small region. But this is now confusing, because I started off with everyone's standard black hole introduction to black holes as confusing and menacing and fundamentally, black objects. And now I'm saying that we've explained a source of X-rays via black holes. So how have these X-rays got there? Well, what happens is that material falling towards a black hole forms what's known as an accretion disk. It becomes very hot, partly through friction, because there's a lot of material in these disks, and partly just because it has to convert its kinetic energy into heat to be able to fall down onto the black hole. And so on lots of different scales in the universe where you have a black hole, you have a disk of material rotating around it, and you get this characteristic signature. If you split up the light into a spectrum, you get this double peaked signature that tells you that there's rotation. And so what we're seeing is light from the material that's falling into the black hole, not the black hole itself. And this is a very efficient means of creating light in the universe. If I take some matter, some hydrogen or something, and I form a star, over the course of the star's lifetime, about 1 or 2% of the energy that's in that gas will be converted to light. But if I take that gas and I throw it down onto a supermassive black hole, about 10% of the energy gets converted to light. So if you want to light up the universe, paradoxically, you need to make black holes. And they do a really good job of this. As telescopes got bigger in the 60s and 70s, people started to find what were called quasars, quasi-stellar objects, these distant objects that appeared to just be point-like. They were later found to be embedded in galaxies. But what these are the glow of material that's falling down onto the black hole that we think lurks in the center of every galaxy. This is the nearby galaxy M87. You can see it's got a bright nucleus, and it's also got this jet of material that's coming out of it. This is material moving at about 99% the speed of light, and it's material that's had a lucky escape, that's been involved in this accretion disk, caught up in a magnetic field, and accelerated away because of the extreme conditions that exist around the black hole. So M87 is an active galaxy that has this jet, but all galaxies, we think, have black holes at their center. We've even taken a close look at two of them. You may know about results from a project called the Event Horizon Telescope that used radio telescopes across the world, from the South Pole to the Atacama Desert to here in Europe, to create the most famous fuzzy orange donuts in all of astronomy. These are images of the region around the black hole at the center of M87, but they've also taken a picture, or they've also done these observations for our own galaxy. So M87 is a much bigger galaxy, it has a much bigger black hole. You can see on the left there's the donut. You can see Pluto's orbit to give you a sort of scale. And if you zoom in, there's a much smaller version at the center of our galaxy. So this orange donut is about the size of Mercury's orbit. And the best way to think about this, if you see these images, this isn't a picture of the black hole. This is a model. It's a reconstruction of what we think is there based on what these many radio telescopes have seen. But it's true that this dark region is the shadow of the black hole. So within that is the event horizon, the region that you can't cross without becoming doomed to fall into the black hole. And so we're really seeing the geometry of the disk and how it changes over very small scales. Einstein would have been astonished. We can now not only detect these gravitational waves, but we can see the material that's falling into the black holes. And when we put all this together, because black holes exist at the center of galaxies, we've even begun to realize that they may have been there right at the beginning. So this is the JWST, our new and wonderful infrared telescope that launched with a golden mirror into space a few Christmases ago. It's been taking a look at galaxies in the early universe, and it's been finding that some of them, in particular this one, Sears 1019, has a black hole at its center. We see the energy from gas that's falling down into it. But we see it as it was just half a billion years after the Big Bang. And it's already got a black hole that's 10 million times the mass of the sun. It's already bigger than the one around our galaxy's center. And so it's clear that these black holes can assemble early in the universe's history. And it may be that they form first, and then the galaxies that we go on to enjoy today form around them. There's a lot more of that story to be unpicked. And one of the ways we're going to do that takes us back to gravitational waves, because so far I've talked about experiments like LIGO that exist on the surface of the Earth that have arms of an interferometer that are 3 or 4 kilometers long. And that means they're sensitive to the frequencies that are emitted when things that are 1, 2, 10, 20, 50 times the mass of the sun collide with each other. But the black holes at the center of galaxies are bigger. They're what we call supermassive black holes, because that's quite a fun name to say. And those are 10 million times the mass of the sun, a few million times the mass of the sun. In the case of M87, a few 100 million times the mass of the sun. And so the gravitational waves that are emitted when they collide, when two galaxies merge and presumably their black holes collide together, they exist on scales of perhaps thousands or millions of kilometers. And so the solution is to take the same experiment of flashing light in different directions, bouncing it off of mirrors and having it come back to a single point, but to do that in space. The European Space Agency is working to launch in about 10 years' time what's called LISA, which is going to have 3 separate spacecraft, millions of kilometers apart, flying absolutely in a precision formation, keeping their distances the same, so they can bounce lasers around and they can detect the merging of very supermassive black holes, hundreds of millions or even billions of light years away. It's an astonishing bravura piece of physics. To do this, you've got to understand the black holes, you've got to solve the equations of general relativity so that you can predict what the chirp is going to be like. You've got to sort out the engineering so that you can fly these spacecraft millions of kilometers apart, such that their distance is always the same. And then you've got to do the data analysis and the statistics to convince yourself and your colleagues that it's real. It's an enormous adventure in physics and engineering, and we're right on the cusp of being able to tell a new story about these things. But that brings me back to my tossing and turning in bed on Sunday morning, because eventually I did what the rest of us do and turned to my phone and started scrolling through, in my case, Blue Sky, and discovered there was news. There was news from this place. This is the Meerkat Array in South Africa. It's the beginning of a project called the Square Kilometre Array, which is a grand adventure involving putting radio telescopes across a large chunk of southern Africa and Western Australia to do things like detect every galaxy in the universe all at once. But Meerkat had been working on a particular project. It had been looking at those pulsars, those neutron stars with jets, and it had been monitoring about 100 of them for the last few years, scattered right across the sky. And pulsars are clocks. They pulse every time that lighthouse beam comes past us. And they're very reliable clocks. And so if you monitor lots of them, and a gravitational wave goes past, if a ripple in space-time crosses the solar system, you catch it in a delay from some of your reliable pulsars. It's an incredibly difficult measurement to make because you can't watch them all at the same time and because you don't have as many as you'd like. But if you're careful, you can predict what this signal will look like. And while we haven't yet got so far as detecting a single gravitational wave in this way, What's been detected by other experiments that was announced last year and now confirmed for the first time independently from Meerkat, just in time for this lecture, fixing my problem that I didn't know how to start or end this, is the background of gravitational waves, the wobbling of the sea in which the Earth sits, because it turns out the classical idea of our planet moving smoothly through space is wrong. We've measured what happens instead. We live on a choppy sea of space-time in which gravitational waves from countless mergers of black holes in countless galaxies for the whole history of the universe over the last 14 billion years is rippling past us all the time. And we've just got to the point where we can measure that and realize that we're standing on this shaky, theoretically interesting, gravitationally unstable sea. And I get to tell you about it. Thank you very much.